Hello, this is Mr. White, and this video is on using the change of variables method, also known as U-substitution, for definite integrals. Here are our two exercises for this video. Let's get to it. So I'm going to go a little bit more quickly over the parts that have already been covered in previous videos and previous lessons. I'm going to rush through those a bit. So we should be pretty comfortable with determining that u is going to be that expression under the radical most times. Not 100% of the time, but most times that works well. So the 2x minus 1 is covered. In general, I recommend doing the dx next. So let's say du over dx, the derivative of 2x minus 1 with respect to x is going to be 2. We'll multiply both sides by dx and then divide both sides by 2. Let's cover the x next. So if we just rearrange this equation, we can get x by itself and get x equals u plus 1 over 2. And if this were an indefinite integral, we'd be done. But since it's a definite integral, we also need to address these two numbers here. Keep in mind that this is an x value. This is x equals 1 and x equals 5. So if I write those two values here, x equals 5, x equals 1, I want to replace those also with u values. So let's use this equation here to figure out what the corresponding u values would be. So when x equals 5, then that means that u would equal 2 times 5 minus 1, or 9. And when x equals 1, that means that u would then equal 2 times 1 minus 1, and it would turn out, coincidentally, to also be 1. So all the pieces are in place. Let's go ahead and u-substitute. For this x up top, we'll replace that with a u plus 1 over 2. So u plus 1 over 2, and that's going to be all over root 2x minus 1. We'll replace that with root u. This dx here, we'll replace that with du over 2. And finally, the integral with the limits of integration, we'll replace that with integral, and then just for emphasis, I always like to write u equals 1, u equals 9. You notice that in textbooks or other resources, they don't always bother with the u equals, but again, I think that's a nice way to just emphasize that we didn't ignore those limits of integration. Let's bring the constants to the outside, so that 2 in the denominator and that 2 in the denominator will become a 1/4 on the outside of the integral, and we'll still have u equals 1 to u equals 9. I'll next have u divided by square root of u. That's also going to give me square root of u, or u to the 1/2. And then we have plus 1 over square root of u. That's going to be plus u to the negative 1/2. And finally, we have this du at the end. So everything has been accounted for. We'll antiderive. So the antiderivative of u to the 1/2 is going to be u to the 3/2 with the 2/3 in front to balance it out. The antiderivative of u to the negative 1/2 is going to be u to the positive 1/2 with a 2 in front to balance it out, and a plus sign. We'll put the 1/4 on the outside. We've just antiderived, so no more integral symbol. Now we'll do the brackets here, and the u equals 9, and the u equals 1. Now, if this had been an indefinite integral, we would have to. We wouldn't have any choice but to back substitute in, substitute this 2x minus 1 back in for wherever I have a u. But since it's a definite integral, I don't have to do that. And in fact, I can save a little time by not doing it. So just to be clear, for some reason every year there's always a few students who just insist on doing it the slightly longer way. And again, if you back substitute this in, and if you plug in the original x equals 4, x equals 1, it would still work. It's perfectly fine. But we've already substituted in for these new u values here. We've already decided what these new u values were. So let's just plug those in instead. And while we're at it, we'll go ahead and distribute that 1/4 as well. Okay, so here I've already plugged in the u equals 9 and the u equals 1. And I'd encourage you not to grab your calculator. Notice that both 9 and 1 are perfect squares, and that means we can do this in our heads. So looking at just this expression, if I take 9 and take that 2 in the denominator means take the square root of 9. Square root of 9 is going to be 3, and if I raise it to the 3rd power, that will give me 27. And of course, this 9 to the 1/2 power is just going to be 3. And we have even better luck over here. 1 to the 3/2 and 1 to the 1/2 are just 1 and 1 respectively. I guess I didn't really need to say respectively, did I? But let's go ahead and finish this arithmetic. Normally I might reduce this fraction, but since I see another one with a common denominator over here, I'm simply going to say 27/6 minus 1/6 will give us 26/6. And here we have plus 3/2, and it looks like a plus 1/2 at the end, but remember, let's distribute this negative. So it's really 3/2 minus 1/2, and that's going to give us plus 2/2, or 1. And now I will reduce. I'll say 26/6. That's the same as 13/3 plus 1. That's the same as 3/3. And we get 16/3 as our final answer. So as far as checking goes, the great thing about definite integrals is that we can use our calculator to just verify that we got the right answer in the end. So we should always check the original function, the original integral we're given. So if we were to graph x over root 2x minus 1 from 1 to 5, we would get 5.33333, or that agrees with the 16/3 that we got. However, it's also interesting to note that if we had graphed the intermediate function, this function that we got after our u-substitution, and if we had integrated that between 1 and 9, the new u values, we would still get, even though we got a different graph, a different area, we'd still get that same answer, 16/3. So let's go on to our next exercise. Now, my personal preference for this particular problem would be to just unchain rule this and not bother with the formal u-substitution. However, every year there are always a few students who, in the case of integrating trig functions like this, just are more comfortable going through the u-substitution process. So that's what we're going to do here. And while you've gotten comfortable taking the expression underneath the radical and making that your u function, let's also recall that the expression inside parentheses tend to be good choices for u. And in this case, here are the parentheses, and we will say that u is going to be defined as 2x. So let's take a look at the dx next. We know that taking the derivative of u with respect to x, taking the derivative of 2x with respect to x will give us just 2. And you know the drill by now. Multiply both sides by dx, and then divide both sides by 2. So we know that we'll substitute du over 2 for dx here. And finally, let's take care of those limits of integration, which are both currently x values. And I will use this equation to convert them to u values. So if u is 2x, then when x equals pi over 4, 2 times pi over 4 will give us pi over 2. And when x equals pi over 12, 2 times pi over 12 will give us a u value of pi over 6. So we are now ready to do our u substitution. And that is going to give us an integral from u equals pi over 6 to u equals pi over 2 of cosecant of u, cotangent of u, and we'll replace that dx with a du over 2. So let's bring that constant to the outside. Okay, there, this 2 in the denominator was brought to the outside in the form of 1/2. And by now we really should know our trig derivatives well enough to recognize that as the derivative of cosecant if I put a negative in front of it. So negative cosecant cotangent will be the derivative of cosecant. And I also need a negative on the outside to balance it out. So anti-deriving this with respect to u will give us cosecant of u. We've got the negative 1/2 here. And I'll point out, I could have had that negative 1/2 on the outside of the brackets. Doesn't really matter. Either case, we will evaluate at the endpoints u equals pi over 6 and u equals pi over 2. And just like in the previous exercise, we could back substitute in. We could replace the u, put the 2x back in, and put back in our old x values. But it's a little bit quicker. You save a little bit of time by just keeping these current values with u. So let's plug these in. Pi over 2, pi over 6. And we know that sine of pi over 2 is 1, so its reciprocal cosecant of pi over 2 will also equal 1. We know that sine of pi over 6 is going to be 1/2, so its reciprocal cosecant of pi over 6 will equal 2. So we now have negative 1/2 plus 1. That gives us a final answer of positive 1/2. So of course, let's check our answer on the calculator. And we see, sure enough, we get an area from pi over 12 to pi over 4 of 0.5.